Hello everybody. So I want to do some more computations today and then go back to theory, but a different theory. So something about Heisenberg algebras and how to make them examples of the same type of things that we're working with. So so I want to quickly finish the computations that we started last time, and so let me go over it again, hopefully relatively quickly. So this is the same program as last time, okay? Just one thing, it starts with let's input common.m. So common.m is a file that I'm going to carry with us for the next however many classes, and occasionally update it, okay? So, like, to include more stuff. So, just to show you what common.m has for now, well, it inputs another package called no theory, which has lots of stuff in it, but most of it is irrelevant, but the part that's relevant is list of nodes. It doesn't have a list of Ribonauts, and since I care about Ribonauts, here is the list of all Ribonauts with up to 10 crossings. Never mind where I took it from. Then it has the program that brings a node to thin position, and it has the PD diagram of GST48, which is just an example that I keep referring to. And that's all. So let's go back to the main program and input common.m. Good. Oops. Oh, sorry. Why? Oh, because I didn't. Sorry, I wasn't. It wasn't a fresh copy. I was running things before. I'm sorry about that. That was just a. Okay. And then let's input all the parts of the program like before. Here we go. Including this program to convert a PD to a rotational virtual node. Okay? And just as an example, let me remind you, so here is the rotational virtual node corresponding to here is the rotational virtual node notation for the node 6,3, so the third node with 6 crossings. So it has a positive crossing where site 1 goes over site 4, a positive crossing where 3 goes over 8, a negative where 9 goes over 12, and so on. And it has rotation numbers, so in the interval before 1, there is rotation number 0. In the interval between 1 and 2, there is rotation 0. 2 and 3, 0. 3 and 4, negative 1, and so on. Okay? So now suppose, okay, so I remind you that I have the tools to compute invariant. So, like, I've already computed or figured out what's the R matrix, the R element, and what the C element is, and I checked that they satisfy all the identities. So all I need is to compute, okay? So a preliminary to this is just a tiny thing to compute rotation number. So if you have a piece of strand with n rotations, and the piece of strand is labeled I, then the value assigned to it should be Ci to the power n. But we didn't write powers yet, so I have to write powers. So I'll call it rotation on strand I, and with n rotations. So this is defined to be, so if n is equal to 0, it's just the identity. If n is greater than 0, then you invent a new strand with temporary name $, and you multiply this with the rotation with n minus 1 rotations, and then you apply the multiplication rule, and that's just an inductive definition. And likewise for negative n. It's kind of silly, you know, it would have been easier to simply compute it once and for all and set it. So, I mean, if you don't believe me, let's compute what's ROT 1 of 15. Oops, sorry, I forgot to execute this. So what's ROT 1 of 15? Well, I mean, it's just, it's very, I think it's clear how to generalize, right? And then it should be clear how to prove it by induction if you really want it, okay? Anyway, this done, let's compute the invariant of some knot. So, so I've already set lowercase RVK, so rotational virtual knot, to be the rotational virtual knot notation for the knot 6,3. So now if I want to compute the invariant for the knot 6,3, all I have to do is to do the following. When X runs over all the crossings of in RVK, so the number 1, like RVK is an ordered pair, so the first element is the crossings and the second element are the rotation numbers. So all I have to do is to go over all the crossings. For each crossing I find its corresponding I and j, and then if it's a positive crossing I put Rij. If it's a negative crossing I put R bar ij. And then I multiply it by the rotation numbers. So, so you know, here's a way to look at it. So, actually, let's actually use the actual knot we have. So, so we have points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have a crossing where 1 goes over 4. So instead of bothering, you know, instead of writing it in the silly planar way, I'll just write it as a so-called Gauss diagram. I think we haven't mentioned Gauss diagrams yet. A Gauss diagram is just the line, the parameter line, with arrows indicating the crossing. So 1 goes over 4 means that I have an arrow from 1 to 4, and it's with a plus sign. I have another arrow from 3 to 8 with a plus sign. I have another arrow from 9 to 12 with a minus sign. I have another arrow from 5 to 10. 5 to 10. Was it a plus or a minus? I think a minus. I have 11 to 6 with a minus. 11 to 6 with a minus. And 7 to 12 with 7 to 2 with a plus. So it's clear how this funny notation is a notation for a knot. It's not particularly pleasant, but I mean, it's actually sometimes easier to work with. And then there are the rotation numbers. The rotation numbers are 0, 0, 0, negative 1, 4, so 5 zeros, 1, 1, 2, 3, 4, 5, 1, 0, 0. Okay? So what I do is for each arrow, so each arrow is either an XP or an XM. So for each arrow, I replace it by an R, and also multiply in the two rotation numbers to its left. So the one to its left end, to the left of its left end, and the one to the left of its right end. And if I go this way over all the arrows, I end up inserting all the rotation numbers as well. So, so here is how this is implemented. So I take the crossing, replace xp by r, xm by r bar, and then I put to the left, so I put rotation, the rotation corresponding to the list of rotation numbers in position I put it in place I minus a half. So basically I invent a tensor factor called, well, for half spaces, and I put each rotation number at at a half tensor factor. I mean a tensor factor labeled by a half integer. So I put in I minus a half, I put whatever should be there. In j minus a half, I put whatever should be there. Then I multiply I minus a half and I into I, and j minus a half into j. Okay? And this gives me all the R information and all the C information that I need for the node. Okay? And here's what you get. Well, you get a product. Since the node had 6 crossing, you get a product of 6 terms, and these 6 terms contain the R's and the C's as well. But now I need to expand this and multiply. Okay? But each of these is a sum of 6 terms, and I have 6 of them, so there should be 6 to the 6 entries in the result. So let me compute 6 to the 6, and at the same time compute the length of the expansion of z. So, you know, maybe even before that, here's what expand of z looks like when you show it short. But unfortunately, it takes a little while. Oh, maybe this is too short. Sorry. So let's do it this way. Let's do short of expand z, but in 5 lines, not in even, well, make it 10 lines. Sorry, Mathematica doesn't estimate right what. So, okay, so basically, one term will be a product of a's from 1 to 12. Another term will be a product of d's from 1 to 12, but the more interesting terms are the terms in between. Anyway, how long is this? So, you know, it has 51,000 something terms. In fact, now I don't need to compute this. What? Why is it writing 51,000 terms here? But when I ask it the length, it tells me that it's only 34,000. I'm confused. I don't know what's going on. But it's a minor point. Anyway, I now want to compute the invariant. To compute the invariant, I have to take my z, and for I running from 1 to 12, in fact, for I running from 2 to 12, I'm sorry about that. For I running from 2 to 12, I need to multiply tensor factor 1 with tensor factor I, putting the result in 1. So basically, I multiply 2 into 1, then 3 into 1, then 4 into 1, up to 12. And then I just factor the output. I print the output, but factor it. This takes a little while, not too much. And that's the output. So we got something non-trivial, right? This is just the identity, but we got a non-trivial multiple of the identity. This prefactor that appears here is called the Alexander polynomial. And if you don't believe me, let's see the built-in program for the Alexander polynomial. So Alexander of node 6,3 evaluated at t, and it's the same. Sorry, it's the same except it's factored differently. Okay? We'll have a lot to say about Alexander polynomial, but for now this is it. Okay, this is hugely inefficient. If you don't believe me that it's hugely inefficient, we can do the same. So we can go through the same procedure for a slightly bigger knot. But in principle, the complexity is 6 to the power, roughly 6 to the power, the number of crossings, which means, okay, 6 crossings we could do, but we wouldn't be able to do 20. Okay? So, as always, it's better to work with tangles. So, okay. So this is going to be a program that eventually will make its way into common.m, because this is how to do all of these things with tangles. I'm not, should I go through it now, or should I just assume it and move on? I mean, I'm like, how anxious are we to go into Heisenberg algebras?
I would like to know about them.
What?
I would like to know about them.
About that or about Heisenberg?
Heisenberg.
Heisenberg, okay. So just believe me that this is done, okay? So what happens is, in short, instead of, replacing all the crossings by R matrices and expanding and then multiplying, I replace the crossings with each one. I take a crossing, replace it by an R matrix. Okay, then I take the next crossing, replace it by an R matrix, and if the two are adjacent, I can multiply. And then I iterate this. So I gradually replace the crossings by R matrices, and each time I multiply, and that, like before, saves a great deal of time. So, let's execute this, let's enter this, and in fact, right, so actually this should have been highlighted. So in fact, if I do it for the knot 817, which is much bigger, notice how quickly it worked. So I compute z of k for the knot 817. It took practically nothing, and next to it I printed the Alexander polynomial just so that you can compare, and it's the same. Okay? And in fact, just for fun, for all knots with up to 9 crossings, I am making a table of, let's test if the Alexander of the knot multiplied by the unit is equal to our z. Okay? So, and in fact, let me drop the union here, but keep the timing. So this is a table of tests. And this will give us a little bit of information of how good is the program. Well, maybe it's not so good. Well, but we are doing about close to 100 knots. So it's okay if it takes a little time. Oh, and it finished. So first of all, it's always the Alexander polynomial. Secondly, it took 20 seconds. So I can do even better, as always. So instead of taking the crossings at random, I first bring the knot to thin position, again, like we've done it before, and then I call it zf of k. So I bring the knot to thin position, and then I compute its z. So let's see if this improves anything. And hopefully it will. So it was 20 seconds, now it's down to 4 seconds. And I will not do up to 10 crossings, I will just do GST 48. So I mean, again, this should be 6 to the 48 if you're not clever. So maybe it is worthwhile to go through the cleverness that goes in here, because it saves, it works. It's a part of, it's the difference between things working and things not working. Anyway, instead of 6 to the 48, let's see how long it will take. There is a bit of a gamble here, by the way, but because sort of there is some randomness in how thin position works. and it doesn't always work the best. So, I don't know. Maybe it was a mistake. So when I did it at home, it took at different times, it took different times between 10 seconds and a minute and a half. So maybe it was a mistake to do it in class, but okay. So you know what? While the computer is computing, I'll start telling you about the Heisenberg algebra, and then finish this discussion, and then and then go back to the Heisenberg algebra. So again, I'm in the process of, well, we have the methodology, and I want to find better and better algebras. So the next algebra I want to play with is the Heisenberg algebra. It's actually an infinite dimensional algebra, so that seems like, so instead of 6 to the number of crossings, the time should be infinity to the number of crossings, which sounds pretty bad, but we will develop techniques that will make it actually easier, okay? But I first have to make some definitions. So, definition. So, the Heisenberg algebra, I'll use Blackboard H for it, is the free associative algebra. So in general, when I put brackets and then precede it with some symbol, it means I'm going to do the free thing, and the symbol means free in what sense? So this is the free associative algebra with two generators called P and X, but later P and X will mean something else, so I'll call them P hat and X hat, and occasionally I will forget the hats, okay? So, and this is actually consistent with physics notation. So if you've ever taken physics, physicists like to put hats in front of above operators. Modulo the relation that the commutator of P and X is equal to 1. Okay? So in other words, Px minus xp, everything hatted, is the unit of this algebra. Wow, this is the worst I've ever seen. This is like the worst luck. So let's pause it. This is just so bad. So let's stop it. I'll just abort the computation and restart it. And let's see how long it will take this time. Okay? So, I told you what the algebra is. At the moment, I'm not discussing coproduct, and it's not a Hopf algebra yet. But I mean, to get good invariants, it should be a Hopf algebra. Just to get invariants, it's enough that, to get good invariants, it should be a Hopf algebra. Just to get invariant, it's enough that it's an algebra. So I told you what's the algebra, that's it. Okay? Or nearly that's it. I just need to tell you what is the spinning element, the spinor element, and I need to tell you what is Rij. Okay? Oh, so this finally finished. And then I'd like to make just quick comments. First of all, it's impressive that it finished. It took 38 seconds. Secondly, so this is the Alexander polynomial, of GST48, and you can see that it's factored, and that the two factors are related to each other. So in fact, if you look at the coefficients, they are in opposite order. So this is up to a sign. So this is 1, 2, 1, 1, 2, 1, 1, and this is 1, 2, 1, 1, 2, 1, 1. Okay? And I didn't label the signs. Okay? So this is a theorem that we will see later. So theorem, if K is ribbon, then the Alexander polynomial of K can be written as some polynomial f of t multiplied by the same polynomial at t inverse, where f is a, I think it needs to be a Laurent polynomial, Laurent polynomial. And before I make comments on that theorem, I will demo it by computing z on all ribbon knots. So if you compute z on all the ribbon knots, it should take a few seconds. Well, you can just check that in all cases it comes out factored and with the same property. That the factors, the terms appear in the opposite order. So here it's 1, 3, 4, 1, and here it's 1, 3, 4, 1 going backwards. So it's consistent with this theorem. So, so a word about this theorem. So this theorem is precisely what I want, except it fails. So, remember that the big question that I posed at the beginning is GST48 a ribbon knot? And the hope is to show that it isn't. So the hope is to find a theorem that is or a property of invariance that is satisfied by all ribbon knots, but is not satisfied by GST48. One such property for the Alexander polynomial is this property, again due to Fox and Milnor. And we just checked it for all ribbon knots, and we can actually prove it, and later we will. Okay? But we've already verified that, lovely as this property might be, it fails to detect GST48, because GST48 has it too. We wish it hadn't. Okay? So hence, much as we will study the Alexander polynomial and learn to appreciate it, ultimately we must go beyond. So all the games I've done so far and the games I'm doing now are warm-up games for what has to be at the end harder, even harder. Okay. Sorry, questions, comments?
Yeah. About the GS48. So in the polynomial T, could you go up a bit?
Sorry?
Could you go up a bit? Yeah. So in the two polynomials above, one has a 7 and one doesn't have a 7. Is it okay that way?
What? Oh, but I'm going backwards. Sorry. So one is f of t and one is f of t inverse, and you also divide by t to the 8, and I'm not sure which one gets divided by t to the 8. I mean, the factor t to the 8 is I don't remember which factor it belongs to, okay? But anyway, so the 7 is the exponent. So what you're saying is, here we have 8, 7, 6, 5, and over here, if we start from the beginning, we have 1, 2, 3, 4, so skips of 1. Here there is a skip of 3, and likewise here in the beginning, so here at the end there is a skip of 3, and here at the beginning there is a skip of 3. So it's consistent with having this property. Okay? Good. Yeah, so I think I'll stop. I'll put this off and continue with the Heisenberg algebra. So so all I need to tell you are what are Ci and Rij. Okay? So Ci is e to the t over 2. And to be precise, it's e to the t over 2 times the unit. And you have to ask me, what does e to the t mean? Okay? Where am I working? So really, I'm not working with the Heisenberg algebra. I'm working with the Heisenberg algebra to which you adjoin a small parameter t. What does it mean to adjoin a small parameter? It means that you consider power series in this parameter t. So truly, my algebra is the algebra of power series in a variable t with coefficients which are elements of the Heisenberg algebra. Okay? So this really stands for 1 in the Heisenberg algebra plus 1 in the Heisenberg algebra times t plus 1/2 times 1 in the Heisenberg algebra times t squared, and so on. So as a power series, it makes sense. And similarly, Rij is a power series. So Rij is e to the t over 2 times e to the t pi hat minus pj hat times xj hat. And again, what does it mean? This is a power series in the variable t. And, you know, maybe I'll just, I mean, it's really the product of two power series. One you already know how to interpret. And what's the meaning of this power series? So this means 1 plus t times pi hat minus pj hat xj hat. And remember my convention that subscript tell you in which tensor factor things live. So this is really 1 tensor 1 in the tensor factor I and j plus pi or plus p hat tensor x hat multiplied by t minus t times 1 tensor p times x hats okay, where plus, now take this thing and square it. So plus t squared times p tensor x minus 1 tensor px squared. Plus, sorry, divided by 2. Plus, well, and now it continues like the usual exponential function. Okay? Good. Theorem. These elements satisfy these elements satisfy all the required identities. So in particular, R satisfies the Reidemeister-3 move, or also called the Young-Baxter equation, and all the rest. So it's probably possible to prove this theorem directly, but I don't want to do it. Instead, I want to build a technology that will allow me to compute anything. Okay? So I want to build a technology that will allow me to compute arbitrary products of such elements in the metamonoid of powers of this algebra. So I want to build a completely general technology, and then once I have the technology to compute anything, I will apply it to R, or to the Reidemeister-3 move, and hopefully the two sides will be equal. So the proof is greatly postponed. Okay. Sorry, I need more chalk. Okay, but let's start building the technology. So the first thing I need is somehow, I need to turn this algebra from something abstract to something concrete. I need names for the elements of the algebra. Okay, so the key point for doing computation with the algebra before was that we named the elements A, B, C, D, and we knew how to multiply them. I need to know how to name elements. I need names for the elements, and then I need a law how to multiply the named elements. Okay? And the key point for this is the following theorem. So, and this theorem is an instance of the so-called PDW theorem from the theory of Lie algebras. So it says the following. So there is a certain map, let me call it O, or blackboard O, and it's called, or more fully, it's the map OPX. And the map OPX is the map from the symmetric algebra in the variables P and X. So what is the symmetric algebra in the variable P and X? It's just a name for the polynomial algebra in P and X. So it's the set of all polynomials in variables called P and X. And this P and X are not the same as those. They have no hats on them. So these P and X are elements of the Heisenberg algebra, and these P and X are just commuting variables. Variables in a polynomial algebra. So there is a map from here into the Heisenberg algebra, and I just realized that I made a tactical mistake. So let's keep the Heisenberg algebra without the T, but say that these two elements belong to the algebra, to the Heisenberg algebra to which you adjoin T. I just don't want T at this level. Okay? So this map is the map which maps. So the O here stands for ordering. So it's the map which takes products of P and X's, and a priori they come, the P and X's are not ordered. It's a commutative algebra. So it's the map which orders them in the order P first and X later. So it's the map that will map P to the I, X to the J, to P hat to the I, X hat to the J, and again, these are different things. This is a polynomial or a monomial, and this is an element of the Heisenberg algebra. So this is the map OPX. It does this. And similarly, though I will not use it, but equally well, I could have defined OXP to be the map which will map PIXJ to first X, then P. Okay? And by the way, these maps in physics are called the normal ordering maps. And the idea is that in the normal ordering, you first put P and then put X. First you put the P's and then the X's. Except there is the other normal ordering in which you do it in the opposite way. Anyway, so far it's been a definition, not a theorem. So now let's turn it into a theorem. So I'm saying that these maps are isomorphisms of vector spaces. Okay? So I am not sure if I want to prove this or not, because I mean, for the Heisenberg algebra it's easy. Later we will use it for other algebras where it's less easy, but in general it's a named theorem. So it's a PBW theorem. If you Google PBW, you'll find this theorem, and it's true for every Lie algebra, or a variant of it is true for every Lie algebra. So instead of proving it, let me just sort of tell you what it means. Or one thing that it means is that if you have an arbitrary product of P's and X's, so for example, I don't know, if you have P hat, X hat, P hat, X hat, X hat, P hat, the claim is that this is in the image of O, meaning you can write it as you can rewrite it in a way such that all the P's precede all the X's. So you can rewrite it as a sum of things of the form some coefficient Aij, P hat to the I, X hat to the J. Why is it true? It's true because, well, we have a rule how to commute P across an X. We know that P hat X hat is X hat P hat. So if we have a, so maybe it's better to write this in the form X hat P hat is equal to p hat x hat minus 1. So wherever you see a p to the right of x, you can bring it to the left of x at some price. So here you see a p ahead of after an x, and that's the wrong order. So you can you can swap them and pay a price, and then you can keep doing this until all the p's are to the left. And then the thing to prove is that what you get is independent. So here you could try fixing it in two ways. You could start here, or you could start here. And the thing to prove is that no matter how you bring it to normal order, you'll get the same result. That's where the difficulty of the theorem is. Okay, good. So what I will do, so our technique will be, instead of working in the Heisenberg algebra, we will work in the polynomial algebra in variables without hats. And we need to develop techniques to copy things from the Heisenberg algebra to the polynomial algebra. So the next claim is, I want to tell you how to copy Rij. So my claim is that Rij is equal, or if you normal order it, you get that it is the normal ordering of e to the t minus 1, and excuse my manners, it's considered impolite to exponentiate an exponential. But sometimes that's what you get, okay? So times pi minus pj multiplied by xj. Okay? So again, this is a commutative power series in the variable t with coefficients pi and pj, and xi and xj. Well, actually only xj. By applying the ordering map, so really this is the ordering map applied in each tensor factor. So maybe I should be calling it raised to the power aij. By applying the ordering map in each tensor factor, I get an element in hi tensor hj, but everything is power series in t, so adjoint t. And my claim is that this element is the element written here. Okay? And the only difference between them is that t got replaced by e to the t minus 1. Why am I doing this? I'm doing this because, well, while this might look messy, it's actually a commutative object. And I will develop techniques to work with commutative objects that look like this. Okay? So, yeah, I'm sorry, that was a modest class today. We'll have to continue on Wednesday. Okay, see you on Wednesday.